Lecture 4, Part 3. Effect of carbon on steel. Carbon has a very marked effect on the properties of steel. Although we usually only add a 1% fraction, and its effect is very great. This ought not to surprise us too much if we remember that there are more than 10 multiply 10 in 22 degrees atoms per cubic centimeter of metal. 1/10% represents 1 part in 1,000. So 0.1% carbon steel contains 10 multiplied 10 in 20 degrees carbon atoms. Expressed like this, we can see that 1% carbon is really quite a lot of carbon. Here you can see that in creosote the carbon content increases the strength and the strength of steel and yield strength of steel. So also the hardness of the steel increases with an increase in carbon. This figure shows the tensile test plots for two low carbon steels. One 1/10% and 12%, a medium carbon steel 1/4%, and a high carbon steel 0.8%. It can be seen that the higher the carbon content, the higher the load required to fail the material, indicating a rise in tensile strength with carbon content. But we can also see that extension at failure for the sample decreases with increasing carbon content. Thus, increasing the carbon content decreases the ductility of steel. This is extension and ductility for each samples. So for these samples, very small ductility of the steel. It affects this fracture behavior of the steel. Higher carbon steel neck less than lower carbon steel when it fails in tension. Finally, the carbon content has no real effect on the stiffness of the steel, no effect on Young's modulus. Also, you can see in this table. And thus we can see why steel is such an attractive and the most important material for all engineering application. It's one of the few metals which has a good compromise between strength and ductility. It's also very flexible to modify. That is it is possible to greatly alter its strength or ductility, hardness, etc. It's available in abundance, relatively easy to fabricate, and most importantly, very economical. As a result, it's the exclusive choice for structural application in civil engineering. Young modulus stiffness remains the same for all the steel samples, irrespective of carbon content. Environmental implication of steel. A major benefit of steel is its recyclability. It's a relatively easy metal to recycle in a way which requires little energy. As the sustainability of steel and other materials are dealt with in greater detail later. In general, the average life cycle of a building is around 60 years. And here you can see the typical life cycle of an office building. Over the 60-year cycle. When it comes to environmental considerations, the most important parts are the embodied energy at the beginning, including extraction, manufacture, and construction. At the beginning and the end of life, including demolition, disposal, including reuse and recycling at the end. In modern day construction of buildings with steel, certain steps are being taken to reduce the environmental impact of steel. This includes the following: demountable building and manufacturing of site and site erection. Demountable buildings. This is where the structure are erected in such a manner that it's possible to take apart the building structure demount with minimum of tasks. The main advantage is that provided the steel structures hasn't suffered any damage, it can be re-erected and hence reused. For the kind of technology, the steel beams are erected using mechanical fixing, such as bolting, like you can see in this figure. Prefabricated steel structure at the Emirates Old Trafford Cricket Ground in Manchester. And manufacturing off-site and site erection. This is another advantage of steel, is that it can be manufactured or fabricated off-site and then erected on-site. The advantages of such a process: the next: large-scale volume production, pre-engineered to required dimension, precision made to manufacturing tolerances, choice of shape and size, ductile material, zero waste, fast erection time, reduced snaging on site, and also very important quality assured low defect product. We already have seen that life cycle of steel in civil engineering application. And in theory, all steel used should be either recycled or reused, which is a hug environmental and economical advantages. Currently, in UK, for example, at least 85% of steel used in construction is reused or recycled. Furthermore, 99% of structural applications are recycled or reused. And only 1% of structural steel is lost to landfill or rust. So here you can see the typical life cycle for steel used in civil engineering applications, showing how sustainable the material is. From raw material supply, then steel production and manufacture of steel construction products, then pre-construction scrape or use in construction project. Then after using in construction project, end of life cycle and or reuse for new project or refurbishment or post-construction scrape, and then repeat of steel production and repeat all the cycle. Here you can see some example using different types of steel and how are different type of steel used. For example, low carbon steel contains iron less than 0.25% carbon and properties strong, easy to work and shape, and uses car bodies, buildings and bridges. The next type, high carbon steel, contains iron more than 0.5% carbon, very strong, brittle and hard to shape. Uses tools, knives and snowboards. The next type we already know, yes, stainless steel contains iron, chromium, nickel and carbon. Their properties, shiny appearance doesn't corrode, and uses cutlery and paints, medical instruments. Titanium steel contains iron, titanium, lightweight, resist high temperature, and uses in aircraft and spacecraft. Tungsten steel contains iron, tungsten. It's very hard and resists high temperatures. uses for high-speed cutting blades and tools. Allowing different combination of elements creates a different type of steels with an amazing range of properties and uses. Now the question, which type of steel is each item made from? So, which type of steel is each item made from? A low carbon steel. Of course, for car body. High carbon steel for sword blade. Tungsten steel for rotary saw. Titanium steel for airplane wing. And stainless steel for culturing. And what's so clever about smart alloys? A smart material can change one or more of its physical characteristics under the influence of an external impact. Shape memory alloy is a type of smart material made from metals that returns to its original shape after being deformed. Nitinol is a type of shape memory alloy made from nickel and titanium. This material can be used to make a pair of glasses, then remembers its shape and doesn't break when crushed. And now I would like to perform summary activities with you. So, glossary. Alloy, this is a mixture of a metal and at least one other element. Blast furnace, a tall oven used to extract iron from iron or by burning it with carbon at high temperature. Or a naturally occurring solid material from which a metal or valuable minerals can be profitably extracted. Brass, an alloy of copper and zinc that is used for ornaments. Corrosion, the destruction of a metal caused by reactions with chemicals in the environment. Ductile, the ability of metals to be strained into wires. Electrolysis, a process that uses electricity to extract or purify metals. Malleable, the ability of metals to be bent or hammered into different shapes. Native, the natural occurrence of a metal as an element in the environment. Ore, a rock that contains a metal combined with other elements in concentrations that makes it profitable to mine. Rusting, the specific name for the corrosion of iron and iron-containing alloys, such as steel. Shape memory alloy, a type of alloy that can return to its original shape after being deformed. Solder, an alloy of lead and tin that is used in electronics. And steel. Very easy. An alloy containing iron and other elements. How quickly can you unscramble anagrams of words about metals and alloys? So, what is this? Blast furnace, corrosion, solder, malleable, native, ore, alloy, breast, shape memory, a type of alloy that can return to its original shape after being deformed. So, it's shape memory. An alloy of mercury that is used for dental fillings. So this is a amalgam. The ability of metals to be drawn into wires. Ductile. A tall oven used to extract iron from iron or by burning it with carbon at high temperature. Blast furnace. A mixture of a metal and at least one other element. Very easy. Alloy. An alloy containing iron and another element. Oh, steel. The destruction of a metal caused by reactions with chemicals in the environment. Corrosion. An alloy of mercury that is used for dental fillings. Amalgam. Brass, an alloy of copper and zinc that is used in ornament. The ability of metals to be drawn into wires. Ductile. A type of alloy that can return to its original shape after being deformed.